This is chapter 6, problem 5. It says at a ball game, consider a baseball of mass m equals 0.15 kilograms. That falls directly downward at a speed of v equals 40 meters per second into the hands of a fan. What impulse Ft must be supplied to bring the ball to rest? So the impulse F times t, and I should write that actually in the front. So impulse Ft must be supplied to bring the ball to rest. If the ball is stopped in 0.03 seconds, what is the average force of the ball on the catcher's hand? Now we're supposed to figure out what the impulse is. The time is given, 0.3 seconds. 0.03 seconds. So time is given, but they're asking for the impulse and they're asking for the force, and with just that one equation, with having two unknowns in here, it's not going to work. But there is a second equation that says that the impulse is the change in momentum, delta m times v. Notice that the units would be the same, kilograms meters per second, and this one here is Newton seconds, and when you resolve that into mass times acceleration times time, you also come up with kilograms meters per second. So the change in impulse, well, those numbers we have given, it's 0.15 kilograms times 40 meters per second, and I actually don't need that delta there, get rid of it. I need a little bit more space. This was supposed to be an equal sign. And the difference is the momentum that the ball has right now minus the momentum it has when the fan has caught the ball. Well, at that point it has a momentum of 0, so I just subtract 0. I still write it there to show that we have a difference here. If I didn't write it there, somebody would question, well, what happened to the delta, the difference? Okay, anyway, 0.15 kilograms times 40 meters per second. 0.15 times 40 is 6.0, and the units are kilograms meters per second as the impulse. Now we use that result, and we're going to do 6.0 kilograms meters per second equals the force times 0.03 seconds. And when we do that, I think I will write this nicely actually, in the meaning of that I will do an algebra step. I would have a force equals 6.0 kilograms meters per second divided by 0.03 seconds, and therefore I come up with 6 divided by 0.03. Do that on your calculator and you do come up with 200, and then we would have kilograms meters per second per another second, which is the same as newtons, so 200 newtons, or in the neighborhood of 40 pounds. That's quite a force that the person catching the baseball has to exert in order to, well, catch it. Problem 7, which says a railroad diesel engine weighs 4 times as much as a freight car. If the diesel engine coasts at 5 kilometers into a freight car that is initially at rest, so here we have velocity 5 kilometers an hour, that is initially at rest, how fast do the two coast after they coupled together. Notice that they didn't give us the mass of either one of them, but only saying that the diesel engine is 4 times as heavy. Actually, that's sufficient. If we have the ratio of the two to each other in their mass, the answer will always be the same, no matter what the individual masses actually are. I nevertheless like to attach a value to it, so let's assume that the freight car has a mass of 5,000 kilograms, or 10,000 pounds roughly. Therefore, the diesel engine has a mass of 20,000 kilograms, 4 times as much. And as I said, I made up these numbers just to have some numbers to work with. Okay, the before and after the collision, the momentum is conserved. So before the collision, we have 20,000 kilograms times 5 kilometers an hour plus the momentum of the freight car, but it's at rest, so its momentum is 0. After they have collided, the two of them are stuck together, so they have a momentum of 25,000 kilograms times whatever velocity. So basically what we're going to do now is we multiply 20,000 times 5, divide by 25,000. Times 5 divided by 25,000, and we come up with 4 kilometers an hour. And when we look at that, that would make sense, because the diesel engine in colliding with the freight car has to be slowed down, so going on from 5 to 4, and because it has much more mass, much more momentum, it's not going to be slowed down that much by the freight car. Problem 8, which says a 5-kilogram fish swimming 1 meters per second swallows an absent-minded 1-kilogram fish swimming toward it at a velocity that brings both fish to a halt immediately after lunch. What is the velocity of the smaller fish before lunch? So we have mass equals 5 kilograms on the big fish, and v equals 1 meter per second, and I may want to label that a plus 1 meter per second because he's swimming to the right. And then the small fish has mass equals 1 kilogram and a velocity that we're supposed to figure out that he's swimming in the opposite direction, that means to the left. So we know that's going to be negative, we just don't know how much. I believe we can already look at it and conclude that that velocity is going to be negative 5 meters per second. The proper way of doing it is to say, okay, the big fish has a momentum of 5 kilograms times a velocity of 1 meters per second, while the little fish has a momentum of 1 kilogram times a velocity of negative something meters per second. And now they collide, and that momentum is being conserved, and that momentum in fact comes out to 0. So after the collision it's going to be 0. Before the collision it's also going to be 0, because the center of mass between the two is the same, and the momentum of the big fish going to the right and the momentum of the little fish going to the left just equal each other, cancel each other. And then we go in here and we figure out, that of course is 5. 5 times 1 plus 1 times negative 5 comes out to 0. So minus 5 meters per second.